Let me start the recording. I think that should work. All right, so this is a layout. Normally, most of the material is here, and then you can see today is Monday, the 8th, and that's what I was planning. Under overview, you should be able to see the syllabus. Inside the syllabus, this is what we mainly talk about today. If we have extra time, we'll pick up chapter 5. Read it together to say if there's any question that you might have. Okay. So the syllabus started with class information, instruction information, meeting time, which is classroom. The required textbook is the same book as what you had last semester. If you already have the book, then the same book. We all had 4701 last semester. The description was in the catalog, the course catalog. The learning outcome is continue from where we left off. We had a bit of chapter 5 and then chapter 6, 7, 8, and 9. So we would be using the chapter 5 through 9 for this semester. Last semester we did chapter 1 to 5, and then we start where we left off in chapter 5 and continue on to chapter 9. The first 4 chapters mainly focus on probability theory. We have discrete probability, we have continuous probability, and then this semester we focus on statistics. The learning outcome, they were the joint and marginal probability. They are from chapter 4 and 5. Mean variance and correlation coefficient are chapter 4 and 5. Chapter probability is chapter 5, 7. Also testing is chapter 6. The Wilcoxon test, I think is 7 or 8. The likelihood ratio test is in the hypothesis testing chapter. Inferences calculation, it ranges from 7, 8, 9. For the relation between 2 variables, that is 9, 8, chapter 8 and 9. And we were supposed to be able to try to learn to use appropriate technology. So in this course, we are going to do a little bit of programming. Have you guys had any programming classes before? Okay, so that shouldn't be much different. So we're doing the command line programming language for statistics. It's called R. I think R is very similar to SCS, to SAS. I don't know. SAS is a commercial product, commercial software, which costs us a few $100. So we use the free open source version of it, which means it should be free, and then I try to make it as straightforward as possible. Basically, any computer language is a way to command the machine to do things that we want to do. The reason we as human beings need to use machine is because we want to save time. Reason. All right, course policy is similar to what we had last time. We hope that you guys all attend classes regularly, so you'll be able to keep up. You know what's going on in class. There's no intervention, no distraction in the classroom. So basically, those are some routine statements about the class environment. Then this is a grading. It looks a little bit schizophrenic, but they were supposed to line up. And these are the percentage distribution. it's different from last semester. Yes. So this class we are going to do small quizzes rather than big tests. So we will have homework assigned from the book, giving quizzes every other week. So there's no quiz this week, but there will be quiz next Wednesday. And next Monday, we'll talk about any questions you might have about homework questions. The quiz will be selected from the homework questions. That's the idea. That means the quiz will be more frequent. And also, I will try to make the quiz as short as possible. Like sometimes it's just one question, sometimes there's two questions on the homework. So if you did do your homework, you should be able to do okay, even if you make small mistakes. But since the quiz are homework question, essentially there shouldn't be a surprise question on the quiz. It's kind of a checking point to see if you did do your homework well. Question. All right, so we will have a midterm that acted as a major exam. So we'll have a midterm, we'll have a final exam. So we have the low stake. The quizzes take I guess all the quizzes together counts as the same weight as one big midterm. So the quizzes are frequent but small and less time consuming. I'm trying to use frequent quizzes to replace a big test. That way on Wednesdays, I have time to talk about materials. So I'm hoping to gain more class time. And so that hopefully the quizzes and tests take less time than the major tests. In the past, I did 4 major tests, and then it takes a lot of time because we gotta have one day to review for the test and then one day to take the test. That's one whole week out of the whole semester. The whole semester is roughly like 15 weeks. If you have 4 tests, you're taking 4 weeks out of the whole class, the whole semester. That leaves very little time to study. So I decided to use quizzes. That way on Wednesday we have a short quiz, and then we can talk about whatever material we want to continue to talk about. Right. So any question? Right. There'll be a final exam which carries the same weight as a midterm. The homework questions are from the book, and that's really the type of question that will be on the quizzes. Class participation, basically attendance. Any question? So this class I did try to do a slightly different because I have no online exam, so we don't get to do the homework. In last semester we have online homework, and then the homework system tells you right or wrong. And this semester we have to take the textbook as our source of the homework questions, and that slow down the grading process because you have to wait a week or 2 weeks after to have your homework back, and then so the quiz is kind of another way to force you to do your homework. Any question? Right. Again, I do value attendance, so that's my attendance policy. I'm still going to use the clicker as a way to collect answers and confirm whether we are on the same page. Our homework will be assigned every day. We talk about new material. We'll be assigning homework from the book, and we'll talk about any question you have for those daily homework. And then we'll have quizzes to assess them. If you need extra help, you might turn to me or anyone in the class, or go to the math lab if anybody has already taken this class. It's an upper level math classes, so it's a little bit hard to find people that can help you. I guess if you have a peer that used to be able to explain things well enough, I mean, maybe you guys can study together or can ask for help. Otherwise, you can ask for help from me or any other math faculty that you feel comfortable to talk to. There are quite a few, like Michael Joseph. He's in the math lab a lot, and I'm in the math lab. I volunteer to have all my office hours, student hours assigned in the lab. So you can see me there very often, ask questions. Other math faculty that you had classes before, feel like they're easy to approach, then just go ahead, ask question. So if you need extra help, feel free to use any other campus source as your network, as your source of information. This is an academic honest policy on cheating, late work. As far as homework, I'm opening up the Georgia View course tool assignment. That's really where I'm gonna collect homework. Like the first one probably will be section 5.3. That's the first homework, because we did 5.1 at 5.2 last semester. So we're gonna start picking up homework from 5.3. That's 100 my system. Let's see, so that's really where you're gonna find places to submit homework. So there will be multiple Dropbox to drop your homework there. That way, whenever your homework is ready, you scan them and then submit it there. That way, you don't have to turn in the paper homework. They are on paper because you're gonna write out your solutions. But in this way, I get to see your solution and you get to keep your work that way. If I finish grading it, you feel like the grading is wrong, we can talk about it. You have verification, you have proof that you did your homework this way. If I did it wrong, you can always, you can argue your case, you can talk about it. I mean, I have the solution, but I can't guarantee I'm 100% right. Sometimes the book is wrong, sometimes my calculation was wrong. So even if the question was graded, you still have opportunity to find out what's the true solution. That was right. So since these were submitted online, so I don't have a really firm late date, but then the quiz is really assigned right after that week the material was done. So if it's more beneficial to finish all your homework on time. Like we assign homework this week, you're supposed to finish it next week by Wednesday. And that's why the quiz will be over those material. If you didn't do your homework, you're probably not gonna do well on the quiz, right? So and that's kind of the quiz is kind of way to forces you to do homework. But then as far as time wise, if you wasn't able to submit your homework on time, there's really no penalty as far as me. But if you misses the test, we really don't have major tests. We have quizzes. If you miss a quiz or miss a midterm, definitely come to me to make up the quiz. We can quickly make up the quiz in the Math and Science Learning Center, Sequoia 219. But if you miss the test, if you miss the midterm, I will send to the testing center. Wasn't here, if you're not here on the midterm day, then we will have to make, because midterm is a major exam for this class. That's the way it's setting. Emergency instructional plan, kind of like all those online meetings. If you are not able to come to class, you can click on, like today, you can click on the class meeting link to attend classes virtually. If it works. I mean, I have to fidget with it. So eventually it start working, but I will definitely try to make sure I open up this meeting and record it. Hi, Anthony.
I got you.
We opened up the class meeting link every day and record the class, so then we have something to go on. So even if you miss class, feel free to watch the recording, refresh what was going on, and be updated. So that kind of helps with late work. We don't have to make up the material that was covered in class, and then that also is our way to handle the emergencies. So for us, it's possible to have an online class if we're forced to be off campus. And as you can see, our homework and also they are also submitted online. under postal assignment, and that's where we submit the homework. So homework can be submitted without come to campus, and class attendance can be achieved attending classes. You can attend classes virtually. So that those will be a way to handle emergency situation or not able to be physically on campus if we are not able to physically open the classroom certain days. Any questions? The CARE team stands for Campus Assessment Response and Evaluation Team. This is a phone number, and that was a reporting form. It was for the campus to handle suspicious behavior, things that happen suddenly, and worries, and then anything that you kind of care and worries you, you can report it. And there's a team, which means there's a multiple person and staff. They can handle different. If it's a medical situation, they'll handle with the nurses and doctors. If it's a security issue, they'll contact the police. So anything that concerns you, you don't have to worry about how to handle it. Just report them, and they'll decide what to do. So there's never, it never hurts to talk about it, so that way we can protect the community from any sudden events. All right, disability access. From last semester, I don't see anyone in our class needed the service from disability access. And those are students with disabilities. Sometimes they can have a special testing environment. Sometimes they need a longer testing time. So sometimes they need language support. So, but for us, it looks like right now all 6 students in this class now have that service, do not need service. Ethical conducts. These are for this honesty and then classroom behavior. There's a policy that's already posted for our students, so I just posted the entire statement. The class withdrawal, I think March 22. It was a Friday. That was the last day to drop the class and have a W instead of WF. So that's the stated dates. Grades appeal. Those are the procedures. Students are unhappy with the grades. Academic progression is, I guess, you have to maintain a GPA of 2.0 or higher. Otherwise, there may be academic probation or academic warning. When your GPA is lower than the certain than that number. Also say groups and activity. These are the policy. If you have to attend an event off campus, you have to go to a meeting, if you have to join a competition, there's a lot of situations where you can't be on campus for the class days, and this is our policy. This is Title IX information about sexual misconduct policy. Those are the statement from USG. House Bill 280 is for campus carry of weapons. I think that was the policy, and we were advised to click on that link and read the policy. And that's the entire syllabus statement. Those are the link for all the actual policy. The syllabus can only contain so much. This is already many pages, but there's definitely more things to read if you care to read about them. Any questions? So then we're just trying to cover all the necessary information for standard syllabus, and this is a syllabus for the course. Any question? All right, so if there's no more question, we'll start with the chapter 5. Let me turn this off. Feel free to read about it. If you want to read the syllabus, is an overview under Georgia review under comments. Find that is available for everybody. I stopped printing paper syllabus like a couple years ago, and now everybody can read it electronically, but it's definitely there. even though I'm not printing them. All right, so today we're gonna start with chapter 5. Chapter 5. Putting all the chapters, sections, chapter 5 in a single try to review. Okay, chapter 5 is distribution of functions of random variables. Is plural means that we're not talking about one random variable. If we're talking about one random variable, it would be in chapter 2 or 3. If we're talking about two random variables, it would be in chapter 4. So we're talking about several random variables. All right, these are the list of sections in chapter 5. 5.1 is function of one random variable. For example, we have variable x. Now let's talk about distributions for x squared, which would be a function of x. If you already knew the distribution of x and you want to find out what is the distribution of x plus 2, so that will be a new variable. And what was the distribution of this new variable? That's what we're talking about in 5.1. 5.2 is transformation of two random variables. Basically, it's function of two variables. But instead of having two variables using two variables creating this new variable, we're creating a system. So instead of x1 plus x2 equal to y1, we added y2 equal to x1. So x1, x2 is being transformed into y1, y2. That's why we're calling it transformation. So it's like a transforming two variable system x1, x2 into a new variable system that's y1, y2. That's why it's called a transformation. So 5.3 is random variable, several random variables that involve 3 variable, 4 variable, 5 variable, 6 variable. So we're increasing the number of variables as we go. But then again, when you have a more variable situation, it gets more complicated and you have to reduce down the situation, add more requirements. For example, 5.3, we added one more thing that all these variables has to be independent of each other. Because if they are dependent on each other, they will have a relation, correlation or covariance. Then it will be really, really hard to study their combined behavior. So 5.3, we did simplify things down by adding that independence requirement. 5.4 is called moment generating function technique. It's a technique that we talked about before, but we're trying to show its power when you are studying the distribution of several random variables altogether. So that is where 5.4 is to assist what we're talking about in 5.3. 5.5 is random variable associated with normal distribution. So we want to be able to see if you have more variables, like 10 or 20 or 30. We have a lot of variables altogether. You have what people call a random sample of size n. And then when you have more variables, then you can apply central limit theorem, and therefore you can have normal distribution when all the behaviors are combined. And that's why we bring up the normal distribution, because it's really helpful to study when the random sample size is large. 5.6 is central limit theorem. It's really hanging in the importance of normal distribution. So in 5.5, we're like, if all these variables are normal, then the summation of the variable is normal, then the average of these variables is normal. But there's this situation that all the variables still have to be normal to begin with for the combined variable to be normal. But 5.6 is like, if you have a large sample size, a large number of variables, then according to central limit theorem, the original distribution does not have to be normal anymore, as long as the sample size is large. So 5.6 went a little bit one step further, saying, hey, if your sample size is large, then central limit theorem is guaranteed that you can use normal distribution to study this. 5.6 is approximation for discrete distribution. That is another reason why normal distribution is important, because you can use normal distribution for Poisson distribution. You can use normal distribution for binomial distribution. So many of the discrete distribution now is available for us to use normal distribution to study them. So as you can see, 5, 6, 7, all these sections brings out the importance of normal distribution. 5.8 is actually a standalone, and we're talking about one of the theorems, and in probability theory, it's called Chebyshev inequality. That's the reason why we are able to define convergence in probability. In calculus, many concepts, limits, derivative, integral, they all based on a limit calculation, and limit calculation based on the fact the quantity has to converge. So convergence is a very, very important concept in calculus, but now we've been at a special convergence. It's called a convergence in probability. So it's one of those convergence concepts that only works in probability theory. 5.9, I normally skip it. That's the limit function of the moment generating function, involve a little bit more of the theoretical part. So normally skip that one, but if you're interested, you can study what's if the sample size gets more and more angles to infinity, what is the distribution of that limit? So it's quite theoretical, since that in real life, you can't really make the sample size go to infinity. So n can be 1,000. That could consider as almost infinity, but still a little unrealistic to say n goes to infinity. So normally skip that part, but it's interesting to study nonetheless. All right, so this is really all 9 sections. If you think through them or draw a concept map, you will kind of see the connection from one to another. The more you connect them, the easier for us to understand it. All right, since we're just reviewing it, so we're probably going to start with 5.1, and then if you have any question, no. All right, 5.1 is function of one random variable. So you have one random variable that's we call x, and you have this new variable, which is a function of x. So y equal to u of x. U is a function name. So the ux can be x squared. U of x can be x plus 1. Ux can be square root of x. So this y variable can have different type of definition. But what we are concerned is to find out what is distribution of y if we already knew the distribution of x. So that's what we were doing last semester. And this is slightly easier if we have a discrete case, a little bit more complicated if we have a continuous case. All right, as we're reading this page, do you have any questions so far? So what we were doing in class, we use an example to see how this can be studied. For example, let's say x is a distribution, a uniform distribution between these 8 numbers. I guess if you draw it in the table, it looks like this. So x is between -1, -2, -1, 0, 1, 2, 3, 4, 5. That's a number. Each one of them are equally likely. So if you read the first 2 sentences, you can see this. So for the x, it takes on -1, -2, -1, 0, 1, 2, 3, 4, 8. They're equally likely, so it's 1/8 for each one of them. So the x and f of x, that is the x value and the probability for every x value. So what we see in that table is this definition. Right? So this definition is a function notation. Now here, this table is a distribution table. I really prefer to write things into a table because you can see with one look at it, you can see what's going on. But with equation and formula, they're more concise and also a hidden. To me, a hidden sometimes the intuition behind it. Right, so using the x variable, we're creating this new variable that's called y equal to x squared. So we want to know what is the behavior of y. Right, down here we have the answer, but you might wonder, how do we get that answer? Since y equal to x squared means that for every x value you're given, you square it. So that looks like this. If x equal to -2, y equal to x squared, so y equal to 4. If x equal to -1, -1 squared is 1, x equal to 0, y equal to 0, x equal to 1. And then you have 4, 1, 0, 1, 4, 9, 16, 25. And these are all because of the x value, because y equal to x squared. All right, and then we're matched with the probability. So for the 4, this 4 is 1/8, but that 4 is also 1/8. So what was the total probability for y 4? is 1/8 plus 1/8, which will be 1/4. And same thing for the 1. Y equal to 1 here, y equal to 1 here, which one is 1/8, so altogether it's 1/4. And then all the other ones, they only appear one time, so their probability is 1/8. And that kind of explains this. So for y, which is x squared anyway, for the y value, the distribution of y can be 1, 4, or 0, 9, 16, 25. So for 1 and 4, they have a higher probability. Touch it, which is 2/8, which is 1/4. For the other 4 numbers, it's 1/8. That kind of explains the formula. So this is a formula format of the distribution or function notation for the distribution of y. And here was this table. That's the probability in the table. But in mathematics, we prefer to concise things. So the formula answer is more a formal way to answer a research paper. But the table there really explains why we get the answer. So if it's possible, we prefer to be able to do both. So we know why things works out. And that was the first example in my plan. Any question? Right, so this is the one we can list as a table. It doesn't happen all the time. Here we have another example. That was a Poisson distribution. X has a Poisson distribution. So we have old variable and new variable. The X is the old variable, which is a Poisson distribution with mean 4. So here, if you remember that, that will be a little review if you forget what was the Poisson distribution. So this is your chance to review it. Poisson distribution has a probability for x value equal to x is lambda to the x e to the negative lambda over x factorial. So that was the formula. Right now, lambda equal to 4, so that was the reason that we have this probability. Now, this one does not work if we want to represent it into a table, because we really have infinite many probability value, because we have infinite many x value, x equal to 0, 1, 2, 3, 4, 5, until whatever, until infinity, and therefore y value also have infinite number. So it's impossible to list everything in a table if you have infinite many number values. So we're going to have to work with formula, and the way we can have the appropriate formula for y, because is through a substitution, and that's something we will be doing many times. Substitutes get our distribution. I'm just hoping that we're able to copy it. Question. So like what we have here, that is the distribution for x. And we're hoping to write something similar for y. Okay. So we are hoping to write g of y. Right, and this is for discrete distribution, so this is actually a probability value. Essentially, we aim to try to get larger. It's supposed to be a probability that the y equal to the number y. So the first y, the capital Y is the variable, second y is the number. So since y equal to x, y equal to root of x, so that is a probability that the root of y, root of x, y equal to root of x. So that means root of x equal to y. Right, we're looking for a probability calculation about this. This is a probability of calculation. So the variable is y. Just like the variable is x in the probability formula for the random variable x, right? So the answer should not have the x, should have the y. But what is this one exactly? That one is equal to the probability that the variable x equal to x, right? Now, if you have this probability, that probability is probability that x equal to y squared. So if we combine these two, the x's are variable, and this is the formula. But if you look at this one, this is a variable, this is a number, and that was variable. So your calculation will be kind of like a substitution. This is your probability calculation. Now, how do we calculate this probability exactly? If the variable is x, this is your formula. Now, if the variable is y squared, and what will be your formula? You have to replace the x by y squared. You replace this x by y squared, and that also because the x equal to y squared is the inverse. Y equal to root of x is a transformation from x to y. So x equal to y squared is a transformation from y to x, right? So we would have our x substituted with y squared. So we have y squared factorial, and then we replace that x by y squared. So 4 to the y squared, and this is e to the negative 4. That one just a number. So that's how we did this calculation, kind of the same calculation as in the book. I'm just trying to illustrate the process of how do we get the formula from x into the formula about y. Question. Okay, so essentially we did a substitution. We substitute in the original probability formula, we have x. In the new probability formula, we need a y. So there is a probability, this is the same probability. So we will substitute the x with something about the y. From here, you know the x equal to y squared. So x and y squared, they are identical. So you're going to substitute this x by y squared, substitute that x also by y squared, and then you're done. Because that was a probability, and this is the same probability calculation. So basically, you go from one probability to another probability, except this probability has a variable y represents x. So what we always did is substitution using the inverse transformation. This is how do you calculate y. This is how you calculate x, which is doing the inverse function. Any question? All right, so as you can see, if you're gonna go from one probability distribution to a new probability distribution, you have to find out what is the inverse. Substitute that inverse into the original probability formula, you're able to get to the new probability formula. That's the underlying idea. So we try to make sense of the process. That way, it will be able to do the same calculation for facing a new question. All right, so these are examples for the discrete case, and you can see even if this probability is a binomial distribution, you can do the same substitution. If y equal to x, root of x, if x has other distribution, a uniform distribution, so any distribution at all, a substitution works out. Now let's move on to continuous case. Suppose x is not discrete. Therefore, you're not able to calculate the probability. Like discrete case, these f of x is a probability, therefore the g of y is a probability, and therefore these are all probability. But if it's continuous case, we cannot calculate probability x equal to x, because in continuous case, probability x equal to a single number will always equal to 0. So we can only calculate probability x less than x. We have to calculate the probability of a variable within a certain interval rather than equal to a single number. And therefore, continuous distribution often being described by the density function. The density function is not the actual probability value. It's actually the edge of the probability area region. So suppose x is a density function which equal to f of x. Now y equal to ux. Y is a function of x. And now the question is, how do we find out the distribution of y? How do we find out the behavior of y? And there are two possible scenarios. Y could be discrete, y could be continuous. If x is continuous, y is continuous, then we're probably going to look for an inverse transformation. If x is continuous, y is discrete, right? Then the calculation for a discrete distribution has to be done one by one. What is the probability y equal to 1? What is probability y equal to 2? What is probability y equal to 3? So if y is discrete, the calculation of it has to be done by a calculation. I guess you might end up doing a integration of the density function. Is the probability is now. One of the examples will be y equal to 0 if x is positive, y equal to 1 if x is negative. So kind of like that. And then you will end up integrating the positive part of the x distribution, integration on the negative part of the integration. You're gonna do it one by one. If x is continuous, y is discrete, and then the calculation of the probability will be an integration of the density function. Now, if y is continuous and x is a continuous, then to describe behavior of y, we need to find the density. It's not that before. If y is discrete, we don't find the density because it doesn't have one because it's discrete. Then we calculate probability. Calculating probability from continuous case, which is why we have to integrate. Any questions so far? All right, so we do require having a monotone behavior. If u is the definition of y, u equal to y equal to ux. If u is increasing, we can find the density of y. If u is decreasing, we can find the density of y. If u is sometimes increasing, sometimes decreasing, that's more complicated. We might have to separate the cases and then have multiple scenarios. The y might end up being piecewise defined. Right, we look at the simple case. If u is increasing, then to calculate the probability for the cumulative distribution function, which is the probability for y, that is the probability y less than y, because y equal to u of x. Then calculate probability u of x less than y, assuming the u of x have an inverse, assuming the inverse is b of x. Now you calculate probability x less than b of x. Less than b of y, and that b of y is the inverse function. Like I said before, if you want to find the distribution for y, finding the inverse is very important because the b of y now replaces this x, right? So all you have to do is plug in b of y into the density f(x). So you have f of b of y, that is the density function, and that will be the density function is really the derivative distribution function. So this is our derivative. If that's the derivative of the outside function, now v of y is the inside function. You have to multiply the derivative of the inside function, which is what we have to find. So in a way, this is really a chain rule. That's the derivative of the outside function multiplied by the derivative of the inside function. The inside function is the inverse. So if you think of it that way, that's slightly easier for us to remember the process. What we're doing in chapter in 5.2. Let's see an example. All these examples kind of trying to call back or remind us what was some of the common distribution. So this example, we have the original variable that was x. X is a known distribution. Known distribution have two parameters, alpha and theta. If you still remember, alpha is being called the state factor, and theta is called the scale factor. Basically, you got two things that controls behavior of the download distribution. And then we're creating this new variable, y equal to e to the x. So y equal to e to the x, which means that x equal logarithm of y, ln of y, x equal ln of y. So that means the logarithm of y is a downward distribution. So what we're going to do is really substituting the inverse. That's why I'm trying to talk about the inverse. Y equal to e to the x. Inverse is x equal to ln y. So we're going to plug in ln y into the x. So this is ln y, this is x. This x is ln y. So now you get this. You see the ln y is replacing the x. This ln y replacing the x. And then this is all a substitution. So you substitute x in the original density f x for ln y. And then you have to multiply the derivative. Derivative of ln y is 1 over y. And that's really following what we're talking about here. You substitute the inverse to the available density, and you multiply the derivative of the inverse. And that's all you have to do in order to construct the density of your new variable. Any question? And also the boundary follows the same idea. Your x has to be bigger than 0. Remember, x is ln y. So ln y bigger than 0. Therefore, y is bigger than e to the 0, which is 1. So this boundary follow this boundary. That was the domain of the density function. We have the formula for the density function. We have the domain for the function. They'll follow the chain rule, this transformation formula. Any question? So this is one example when the transformation function from x to y is increasing. E to the x is an increasing function, therefore the inverse function, which is logarithm, which is also inverse. Increasing function. If the original function is increasing, then the inverse function is also increasing. So they all have monotonic behavior. This variable that we had, which is right here, is called a log gamma distribution. So y, the y equal to e to the x, has a log gamma distribution. In a way, you were saying this random variable's logarithm has a gamma distribution. That's why it's called log gamma distribution. For this, we have the formula for the mean and variance of the log gamma distribution. Any question? So, all right, and we also defined one more distribution that's called Cauchy distribution, which is related to an angle. You have a uniform distribution x. X is a uniform distribution between negative 90 and positive 90. You can think of the x is an angle. This is a needle that was hanging there, and the needle has an angle with a vertical line. So this angle can be positive 45, positive 90, or negative 45 or negative 90. So this angle that's you got a needle hanging there, the angle is right between negative 90 and positive 90. So this angle, we're using this x to find the tangent of the angle. So x representing an angle that was hanging the needle there. Now y equal to tangent of x. So y is the tangent of that angle. Now tangent 90 degrees is really undefined or infinity. Therefore, y has a domain. Y has a value that becomes negative infinity to positive infinity. But x, being the angle, is between negative 90 and positive 90. Okay. So we're transforming from x, which has a finite boundary between negative 90 and positive 90, to the y value, which has negative infinity to positive infinity. So we're actually converting from a bounded interval to an unbounded interval. Now the question is, if x is uniform, so it's equally likely to be any of those angles between negative 90 and positive 90. What is the distribution for y? So we're going to try to go ahead and find it. We actually, this is uniform distribution. We can define this distribution, the cumulative distribution function here. And you can see this distribution function, the derivative of it is 1 over pi, which is kind of like a 1 over b minus a. That's a, that's b. The uniform distribution from a to b. The density function is 1 over b minus a, right? You kind of remember. All right, so the question is, what is the distribution from y? So what we're going to do is what we did before is we want to find the probability of the y value. So cumulative distribution for y is the probability y is less than y. Y is the tangent of x, so tangent of x is less than y. So x is less than our tangent of y. So this is the probability. And we know that this probability is being given in here. This is the probability. So we're going to plug in the r tangent of y into where the x is. The x plus pi over 2 times 1 over pi. If we plug in there, we get this, right? So that's the cumulative distribution function, but we care more about its density. So we're going to find the derivative of it. So we're going to find the derivative of g of y. Have your CDF. Derivative of CDF is PDF. Probably density function. So finding the derivative of this, derivative arctan is 1 over 1 plus y squared, and coefficient 1 over pi. And that's why we end up getting this. This is called Cauchy distribution, Cauchy density function. And it's kind of the interesting thing because this function is also bell-shaped. It has right in the middle. When the y equals 0, you have 1 over pi, which is the highest point. And then to the left and to the right, it goes down. So it's kind of like the normal distribution, but it's different because I think it has a different variance. Also, the curve is different than a normal distribution. Another thing is if you want to try to find the mean, a Cauchy distribution the mean does not exist. It has median, obviously the median is at 0, right? Y equals 0 is in the middle, so it has a median equals 0, but it doesn't have a mean. If you try to find the mean is e to the y, right? E to the y is integration y times the density. If you integrate, you try to find the integration y times 1 over 1 plus y, that is the integration between degree 1 and degree 2, right? That is an improper integration. You think about calculus, integration of y over 1 plus y squared is infinity. So it does not exist a mean. It does not have a finite mean. Interesting. All right, so that also is another thing to remind us. Mean and mean, they're not exactly the same thing. They're both representing the center of the distribution. Sometimes the mean does not exist. And median always exists. Median is 100% division line, but it always exists. What if U is decreasing? We mentioned that before. Even U if it's decreasing, it's still monotone. You can still find the inverse, even though the inverse is not decreasing. So for example, if U is decreasing, then Y less than Y, meaning that U of X is less than Y. Since this is a decreasing, that X is bigger than, so this is a conversion between these two, between U of X less than Y and X is bigger than By. Once we convert it to inverse of both sides of the equation, the turn direction, right? And we want to try to find a probability that's going to be probability for a continuous distribution is integration. So this, we're going to calculate the probability, you're going to do integration from this bottom value to any value that you want to calculate. All right, so we will end up having to do that. If you want to find the derivative of this function, according to the fundamental theorem of calculus, that this is a derivative, plugging that one into this function, right? Calculus, fundamental theorem of calculus, part 1. So you're going to plug in the inverse function in here. That is a derivative of this integration defined function. And then you have to multiply the derivative inverse. Now, derivative the inverse is going to be negative because the function is decreasing. But a density function cannot be negative. So what do? We put a negative sign there. This derivative is negative. Negative is negative is positive. The reason we add a negative sign there is because we want to maintain the positivity of the density function. Hope that can make sense. So we end up combining the case. So if it's increasing, then you have this and this. All right. If it's decreasing, you have negative. So negative, positive, all we have to make sure is add absolute value sign. So this formula combines the increasing case and decreasing case. So the bottom row is a formula for how we just determine the density function, whether it's increasing or decreasing. Any question? All right. So then there's other cases. What if it's not monotone? What if it's sometimes increasing, sometimes decreasing? Then the situation is more complicated. We have to look at piecewise defined. Like what is when the y is less than this number? What's happening? If y is bigger than this number, what's happening? So we have to find the boundary when the interval when it's increasing and the interval is decreasing, and look at it case by case. So it's a little bit more complicated. Let's see. All right, how are we doing so far? Was it okay? This is a pretty much a review of what we're doing in 5.1. If we are trying to relearn everything, it felt like a whole lot, but since we already did it last semester, not too far ago, so it was okay. But either one, 5.1 and 5.2 have a central idea. That is, if you want to know this distribution of the new variable, you have to make use of the distribution of the original variable. And you kind of tweaking it to find out what's the distribution of the new variable. So substituting the inverse to it, you find a derivative and multiply it, and we're combine all together. Really how it works. So this is 5.1. Then a couple of other byproduct of all these discussion. Number one is if you have a uniform distribution, we're able to find out and you got a function f of x, and you can define a new variable that has the same distribution as the function f of x. So that made it possible for you to determine whatever the distribution function you want it to be, as long as this function is increasing. So that's the first one. And the second one, we went backward, like this is a simulation. One of the purposes of this result is to simulate. Let's say I want to simulate a normal distribution, what to do. And if I want to simulate a normal distribution, so this is made possible, so you can find that inverse function. Another one is the second part, that is if you have a variable x, how do we create a uniform distribution? So they are kind of go back and forth. The first part of 5.1, the first theorem saying you got a uniform distribution, how do you create this new distribution? The second one is whatever your distribution is, how do you create that, convert that into a uniform distribution? This is like any distribution, if you already have its CDF, you can always convert it into a uniform distribution to do it one. And this is how we do it. Any question? So this is how do we systematically construct a uniform distribution? Not as we have computer that actually already coding or computer system software that does this for us. So you're going to simulate a normal distribution. It does it. If you want to simulate a uniform distribution, your computer actually have a language for it. I think it's called R&D and R. Many computer language call them R&D, like random, the first 4 letter random. And this is one of the examples to create a density function. 5.2. A little bit more time. We'll continue next time. So basically, this kind of gives you an example how we're going to learn the whole semester. But feel free to stop me. Sometimes I can be on and on, but if you feel like this is too much, it's time to pause a little. Just let me know, and then we can print out one of the homework questions and talk about examples rather than reading the examples. Are we okay so far? All right. So anyway, syllabus is online, and this file is also on ChurchView. And we're going to continue 5.2 next time we come back on Wednesday. In the meantime, we probably gonna I don't know. We're probably gonna go through 5.3 next time. Hopefully we have enough time to start 5.3 on Wednesday. But that's really the plan. I'm gonna follow through the entire file. The assignment for each section, they were already in the text. 5.3, and the assignment is right here. So that's gonna be our homework that we submit on. Right. Read through this if you have any questions. I'll see you Wednesday. Okay, I hope it's not too hard. Okay. They were here last semester. You were before, right? You can either way. I have this ebook, so I don't have the. I don't need to try either way. I don't think great. Bye. Thank you.